Right, we're going to look at ANOVA with more than two groups now. Okay, so let us move on. As opposed to just two groups, which gives us, we can use a t-test or ANOVA. With more than two groups, three groups as we're going to use, we have to use the ANOVA model. All right, so here's the scenario. We've got store configuration upgrades. We have upgraded a set of stores, of similarly sized stores, to either a digital, millennial, or traditional look and feel. So, is there a difference? Do these factors, do these different upgrades have an impact on turnover? And is this impact different between the stores? So, effectively, which upgrade is more effective is what we're trying to determine here. Now, in this case, the hypothesis for the null hypothesis is the same as for two groups. The means, the population means are all the same, okay? More or less, yeah. See, population mean 1, 2, and 3 are all the same, and that's what that represents here. The alternative hypothesis is that there's a difference somewhere. There's a difference in means somewhere. It doesn't mean all of the population means have to be different, but as long there has to just be at least a difference somewhere. It might be that they're all different. It might be that some of the groups are different. But for the alternative hypothesis to be held true, we just need to find a difference in at least one of the groups. But it can just be in one of the group comparisons, okay, one of the group pairs. So yeah, you'll see what I mean. Now there is something called an error rate. It's a compounding of an error rate for multiple comparisons. So with t-test, you've just got one comparison. You've got two groups, one comparison. Okay. Now, so we've established that we're going to accept an error rate of 0.05. That's our alpha. So that means our chances of not making a mistake are 0.95. Okay, we're 95% certain of our testing in this case. So that's okay for t-testing. But when you're comparing a number of groups, this error rate, as you can see, compounds. So 0.95 times 0.95 times 0.95 equals 0.857. So that then, if we think about that means the error rate goes up from 0.05 to 0.14. See? So if 1 minus that is 0.14, and it goes up for the more groups we have, the bigger the error rate. So that's a sort of a probabilistic issue that we've got when you the more tests you bring into your experiment, then the more you're compounding the chance of an error occurring, because you've got more essences, more groups in there in which that error to occur. So what we do is, and I'll explain this one with a proper example. Well, I'll explain the numerics of this in one of our classes. But if we just accept that to be the case, all you need to do is, well, when we compare our means, we can just do multiple t-tests and ignore the issue that I've just discussed there. Okay. However, we can invoke the Tukey comparison method, which is what we're going to do, and you'll see how we do it in the video that I show next, where I actually do the jump thing. So there we go. So yes, it's Tukey or Tukey-Kramer. That's what we're using here. All right. It's a quiz. Why is a Tukey-Kramer test for all pairs recommended instead of the student T? Yeah, as we've just said, yeah, we want an experiment-wise error rate to be 0.05, and you could see there that it was moving up. It went up to 0.14, which is not acceptable. So that Chuki procedure just regulates the what is acceptable when you compound the error rate by by having multiple tests. Okay, so it makes it stricter effectively. If we go back to there, it will sort of reverse calculate the error rate so that our three groups error rate is 0.05, if you know what I mean. We'll look at it in class, I think. Okay. All right. Let's not dwell on this. Thank you. Let's find out how I stop this video, which is here.